blood sugar is
Well, good evening and welcome to another edition of the Tutor Wizard. I'm your host, Tim, and today is lecture number 2 in the series of Introduction to Statistics. Since the spring intersession is already underway, I figure now's the time to get this stuff nailed down. What we're going to do tonight is mostly definitions with a few calculations to illustrate those definitions, because if you're going to understand everything in these lectures, you really don't want to be sitting there going, what did the prof mean by that? Which is not an unusual question to ask yourself. Sometimes these things go by pretty fast. With intersession classes at the university local to myself, it's 6 weeks and several hours a day, Monday to Thursday, so it's easy to fall behind. I haven't quite figured out how I'm going to handle the statistics labs that are going to be part of the course as well, but I'm working on it. Just as a heads up for that, in most of the intercession courses here, be using the software package R. Now, R can be used from the command line, but that also requires a bit of technological skill. I know most students these days have very little, if any, experience with the command line. But if you really want to live the old school ways of computing, that would be what you'd want to do. Typically, though, there's a couple of interfaces that can be used for the statistics labs. Most of the time, they suggest either R Studio, which is kind of a bit more user-friendly, but it's still largely command line driven. There is also R Commander. Now, R Commander is largely coded out of Simon Fraser University. It's got a Canadian connection, yay us. It's very much a point-and-click interface, but it does have a few quirks as well. Not as many quirks as, say, R Studio. And for the average neophyte user, if you asked my opinion, I would say this is your first choice. This would be your second choice. Now, there is another program out there that uses R as a background. I don't think any of the profs are recommending it. But if you have time, I would take a look at this one, JASP, JASP. This is a software interface to R that comes out of Europe. It's nicely coded in a much more modern style. If you look at the style of the interface for R Commander, it's very much a 1990s model. And the interface for R Studio is also getting a little bit dated in that it's probably looks like something you'd find on a computer 10 or 15 years ago. Anyway, R Commander is probably the one you're going to want to use if you have a choice. R Studio may be the one they want you to use. The ability to write code and get the statistics you want out from the program, oftentimes the profs are going to give you help files to do that. I would recommend you take a look at those help files. And I know at the University of Alberta there are also help videos, if that works for you better. Anyway, that's my conversation about labs for now. I'm going to see what I can come up with over the next few days to make this a bit less painful. Maybe we'll do a specific Twitch stream and walk through the use of one of these programs. I'll probably do the R Commander one. I may tinker with JASP a little bit too. I haven't quite figured it out yet. Anyway, that's the preamble I wanted to get out of the way tonight. Far as anything else goes, it's a lovely day here in beautiful downtown Edmonton. Well, I'm not in the downtown. I'm living in suburbia at the moment. But temperatures are getting up there. If you're wondering where Edmonton is, we're just a hair under 55 degrees north latitude. So if you're in Europe, you can probably relate to that if you're in parts of Scandinavia or northern England, I think, northern Britain. Not sure what the latitude for Hadrian's Wall is, but it's got to be up there as well. Of course, we don't have the benefit of the Gulf Stream to moderate the weather, but it is what it is. Well, I suppose we should probably get cracking, because I got about 10 slides I want to go through and talk about terminology, definitions, and some basic computations as well tonight. So let's get into that. Boom. What's a distribution? You're going to hear the word distribution time and time again. And you should understand what your prof is talking about when they use the phrase distribution. So there's two things we're going to encounter in this course. There's the distribution of data, and there's the distribution of events in probability. Nope, we got a break. So there's a lab, what am I talking about? There is a ad running, and that's fine. I'm not surprised by that. We'll just let that run out. Data and events. We'll talk about that once these ads conclude. But in the meantime, we're going to chit-chat. The general biome around this part of the world is what we call aspen parkland. So you got lots of trees. Naturally, there were a lot of tree here. Not the heavy, what's the word? Not deciduous, the other word, for evergreens. You don't have to go very far north or very far west into the foothills of the Rocky Mountains to run into the coniferous forest. But around here, this is aspen parkland, so you have patches of green. You have your typical aspen family of trees. It's actually quite pretty if you go out in the bush, or, meadows for that matter. It's your basic wildlife. Occasional ones that will try to eat you, but that's why you carry bear bells along or bear spray. Mostly black bears around here, so they're basically little cowards. You just got to yell at them a little bit. I wouldn't recommend getting between a black bear and her cubs, however, because all bets are off on that one. Anyhow, we're back from the ad break. So distribution, how can we interpret that? So now none of the definitions I'm going to give you are, rigorous mathematical definitions. I'm giving you working definitions, and I want you to think about the word distribution as equivalent to the word pattern. Statistics is all about analyzing patterns. We can have patterns in the data that we're analyzing. We can have patterns in probability of events. And we're going to have both, actually, because why would I deny you the pleasure of each? So what's the patterns in data? Well, data patterns would be what's the most common occurrence? What's the most common value? That's part of identifying a pattern. Most common value. If we were talking about events, what is the most likely outcome? Now, if we think about games of chance, I mentioned last stream I'm going to talk a little bit about games of chance, especially when we're talking about probability. So if you look at the game of dice, a friendly name is called craps. What's the most likely outcome when you roll 2 dice? Well, the most likely outcome is 7. There's 6 ways to get the number 7. You got a 5 and a 1, or what am I saying, a 5 and a 1 for? A 6 and a 1, and then the first dice can be a 1, and the second die can be a 6. So you got 6 and 1, 1 and 6, there's 2 ways. You got 5 and 2, 2 and 5, now we're at 4, and now you can have 3 and 4, and 4 and 3. These will all give you the magic number 7 if you're playing craps, and you don't want a 7 in craps. That means you've crapped out, and that means you're going to lose, or you already have. So the difference between most common value and most likely outcome is kind of subtle, I suppose, but context is everything in statistics. So this is going back to my comment about careful reading from last stream. Now, what else can we talk about as far as patterns? We want to know what the minimum and maximum is. What's the smallest and largest? Because from data, that'll give us the range. Well, we can have a smallest and largest outcome as well in probability of events. What's the least likely as opposed to what's the most likely? Again, this is highly dependent on context, of course. Some games doesn't make sense to have the least likely, but every game does have a most likely outcome. We technically call that the expected value. Most common in data patterns can be a couple of different words. You could have means, medians, modes, and we're going to talk about all three of those tonight. So patterns in data then can be used to describe the data, which of course is going to lead us into our conversation about descriptive statistics in probably the next stream. Tonight we'll be done with definitions, and then we're going to get into discussion about how to describe data. What else can we say about data besides where's the center? How far does it spread? What's the least likely outcome? What's the most likely outcome? These are all parts of the interpretation of the word distribution. Keep that in mind, because when your prof is talking about distributions, that is no doubt what he or she is talking about. Now, if this was a bit of a more hardcore math class, in mathematics, distributions can be functions, but that is not a context that's applicable to first semester statistics. We're never, ever going to talk about it like that. If we wanted to get hardcore, one of the distributions, just as an example of what we're not going to do. Sorry, I have to tell you this. I don't have to, I just want to. Maybe it makes me feel good. I don't know. One of the most common distributions is the standard normal distribution, or usual bell curve. Well, the mathematics that you won't have to deal with involves calculating the area below this curve and above the x-axis. And that is the integral from negative infinity to positive infinity of e to the negative x squared over 2 dx. And we have the coefficient out front, 1 over the square root of 2 pi. And this whole thing is equal to 1. You won't have to do that unless you plan on making making your minor or your major a statistical one. This is simply the math that we don't talk about. Recall from the previous stream I said you don't need to think about this course as a mathematics course. I want you to think about it as an arithmetic course and a careful reading course, because we're not going anywhere near that hardcore stuff. We're going to keep it simple. Everybody can add and subtract. You get a calculator. And no one's trying to make your brain explode. This other stuff, if you want to make a career out of statistics, that's the way to go, but that's not what we're going to be talking about over the next couple of weeks. Okay, so distribution, patterns. Remember that. That's all it has to be thought of. Just think about that. That's all it has to be. Let's look at the next slide. Building on the idea of patterns. Skewed distributions versus symmetric distributions. Well, I've already shown you one symmetric distribution. That was the standard normal curve, the bell curve. And we call a curve symmetric, or a distribution symmetric, if it can be reflected across a vertical line, the vertical axis. So here, the left side over here and the right side are identical. We can fold that branch over here and it'll lay identically on top of the other side. So this is symmetric. But it's not the only way to get a symmetric curve. So this is the standard normal curve. I'm just going to call it normal, mostly because I didn't leave myself enough room to write standard normal. But that's the normal distribution. And the word normal distribution doesn't mean it's the opposite of unusual or weird. It's, well, you know what? There's a bit of a discussion on where that name came from. But Mother Nature loves this bell curve. So much of it appears in the handiwork of nature. So I suspect part of the reason it's called normal is historical and empirical. But we also have the uniform distribution. The uniform distribution would just look like a box. Now, again, there's a middle value, and again, we are symmetric across that vertical line. So this is uniform. If this was discrete data, this would be rolling a die. You're saying what's discrete? I'm coming to that. That's one of our discussions tonight. Now, if this was about rolling a die, there's 1 through 6 on there, right? So we could call this 1, we could call this 2. Now, the average value is 3.5, which of course isn't actually on the dice, but that's the average. So there's 1 there, here's a 2, here's a 3, here's a 4, and here's a 5. Well, guess what? If the area under any curve is exactly 1, and it is, because that's what this thing was all about back here for that particular curve, then if the area here is 1, then this height must be 1 over 6, because width times height is always equal to 1 for the full distribution. We'll beat this up more so when we get into probability, but for now I want this to stand as an example of a symmetric distribution. One you may not encounter, well, you might. I can't say for sure what your prof's going to do because I don't read minds, but if your prof really wants to challenge you, they'll give you some geometric distribution. Well, here's a lovely geometric distribution. It's a triangle. And as long as the area under it is equal to 1, it's a probability distribution. Now, how do you figure out probability? Well, you still have height, and you still have width, and since area is equal to probability, we'll have 1/2 width times height. That's how we'll do it if we need to do it. I'm not going to worry about it right now because that's ahead of us, and we're not going to jump too much. I like to jump around a little bit because these ideas are never strictly limited to one context. So anyways, that's what symmetric means. Whoops, didn't click back to the marker. There we go. So symmetric is done. But what is this skew of which I speak? Well, anything that's not symmetric is asymmetric. And usually for us in this course, it's got a skew. So a right tail skew would look like this. Now, what does a left tail skew look like? Well, it looks like this. Now, here's the thing to keep in mind. It's the tail that identifies the skew. Tail identifies the skew, not the hump. So this is typically the behavior of large outliers here, or really small outliers here. If you were to put this on an x-axis, if I was to label this, this would be 0 and this would be infinity. This would be 0, this would be infinity. Now, there's a characteristic about skews that you really, really need to put on your 3x5 card or your cheat sheet or wherever. You need to know this, okay? There are two measures of center that we need to pay attention to. The median will always be closer to the hump, and the mean will always be pulled towards the skew, towards the upper outlier. So in this example, for a right tail skew, let's write that down here, right tail skew. In the right tail skew, the mean is numerically larger than the median. Over here, when we were talking about symmetric distributions, the mean equals the median. We're going to talk more about this momentarily. Now here, where we have a left tail skew, the median is here, and the mean is here, so the mean is less than the median. So a typical question that can quite often show up on your midterm exam is they're not going to give you the picture, they are going to give you summary statistics, maybe the 5-number summary, and the median will have a number, a numerical value. The mean will have a numerical value. And one thing we can do is look at which one is bigger. If the mean is numerically greater than the median, we know that there's a right tail skew because it has to look like this guy right here. Now, if the difference between the median and the mean is small, there's probably not much there to talk about. So when I say small, if the median was 5 and the mean was 6, yeah, I might say there's a slight skew. If the difference was 0.5, I probably wouldn't even consider it. Now, if the median was 5 and the mean was 10, yeah, there's definitely a right tail skew there. But these questions don't usually come at you in the form of just, here's the numbers, what's going on. They oftentimes give you more information, like, say, a box plot or a histogram. So you never analyze data very often strictly in context of one method. One of the things they tell you when you first learn data analysis is graph the data, because then you can look at the numerical output and you can compare it to the picture. It's just wise. It's just how you do it. Okay, I think we've talked about that enough. Why don't we move on to the next slide here? Next is mean versus median versus the mode. And here's the data set that we're going to work with. Now, here's your first, how do I want to put this? I'm trying to be polite. Most people say, yeah, the mean, if you have average intelligence, that means 50% of people are dumber than you. No. The only time you can say that is when the mean and the median are identical. It's actually the median that tells you about 50%. This is the 50% cut line. Half the data is smaller than the median. The other half of the data is larger than the median. The mean, remember, is just the average. And I'm going to illustrate in a couple of minutes how the mean changes in the presence of outliers and how the median does not. So the mean is just the average value. But remember, unless you have a symmetric distribution, the mean and the median are not going to be the same. And then you say, what is this mode of which you speak? Well, the mode is the most common value that appears. All of these terms, by the way, are called measures of center. And we'll do this spelling of the word center tonight. Okay, so this tells you where the center is. There's also measures of spread. We talked about the measure of spread in the last stream when we talked about variance and standard deviation. We may get back around to that tonight too. Certainly we'll be revisiting that entire concept several times in the next week or so. So let's look at the data here. What's the most common value? Well, here there's 2 2s, but I also have 2 10s. So you can always have ties here. So this is bimodal because there are 2 values that are most common. We are bimodal with modes of 2 and 10. If it was, let's say I only had 1 2 and still had the 2 10s, then it would be unimodal. And if we have more than 2 modes, We usually just say it's multimodal. Now, what does that look like on a graph? Well, it may be that there are two distinct humps. Here's your mode at 2, here's your mode at 10. No smart aleck remarks from the peanut gallery. Tell you what, let's give it a face. Yay. Okay, now it's nice and innocent. Anyway, so bimodal. Mode is the most common value, which is in the data set. Now, what else do we got to talk about here? Now, what is the median? Well, remember, median means exact middle. If you think about traveling down a street where there's grass in the middle, or concrete, or some other suburban blight in the center, that's called a median because it's the center of the road. You'll notice here there are 9 observations here. Now there's a couple of different ways to compute the median. We are going to do this one by eyeballing it. If you have 9 observations, then the 5th observation is going to be the median. So this is the odd number case. So if I come in 4 from this direction and 4 observations from this direction, I find the exact center is the number 8. That's the median. Right there. I'm going to look right there. I better pull this down a little bit. So this is, trying again, Tim. This is our median. And you'll notice that cuts the data into 2 distinct chunks. One thing I didn't put on here, and we're going to talk about it anyway, I think is called the quartiles. Because what is a quartile? Well, if you have a loaf of bread and you cut it into 4 equal chunks, well, the analogy is perfect. We're going to cut this data into 4 equal chunks. And this is where things are a bit different. So now we have a bottom 4 and a top 4 here. So quartiles then are simply the medians of the lower half and the upper half. There are a couple of ways to do it. The way that's relevant to the university here, and I'll probably do the other way at another time, is to find the middle of the bottom half. So we have 4 observations, so that middle is right here, halfway between the number 2 and the number 3. So in this case, we would simply take the average to get the first quartile, and that's going to be 2.5. I'll illustrate the other method at another time. Again, we're going to do the same thing up here. This is 10 plus 12 divided by 2, and this gives us 11. So we have quartiles. They are the medians of the lower half and the upper half. So this is Q1, and this was Q3. It's not the best picture I've ever drawn, but it'll do. Like I said, we're going to talk about this more. I'm just kind of introducing terminology tonight. I will in particular beat this up when we do the 5-number summary, because the 5-number summary will also allow us to understand box and whisker plots. And that's my goal in another conversation. Now, what is the average value of this data? Well, let's do that. I got a little bit of room here. Let's move this up first. So the average then, as we discussed in the previous lecture, is simply add the values up and divide by how many. So let's write mean here. So we know there's 9 observations. So how many, what's the total here? So we have 2 and 2 is 4. And 3 is 7, and 5 is 12, and 8 is 20, 30, 40. Here's 52, 62, plus 5 is 67. So what's our average value? Well, 9 times 7 is 63, so it'll be 7 and 4/9, which is 0.44. There's our average value. Here's a pro tip for you. You don't need a calculator to figure that out. You do the 9 times 7 gets you to 63, right? So you still need another 4. But I know that 1 divided by 9 is 0.111 forever. But I don't have 1/9. I have 4/9, so that makes that a 4, and that a 4, and that a 4. There, you don't need a calculator. I just showed you a trick. Okie dokie. Yeah, that slide got all drawn up, but that's fine. So median, mean, and mode all tell you where the center of a distribution lies. For instance, our bimodal distribution here will still have a center. And that center we can describe, in the way I drew it, is mostly symmetrical. So here the mean and the median will be fairly close, although you'll notice that there's a bit more of a tail going out this way. So it would suggest to me that the mean is slightly smaller than the median. Okay, anyway, that's enough of this slide. Let's move on to next. Census versus a sample. Actually, that one seems a bit out of... Yeah, no, we'll do that. Okay. I'm just going to check something here on Open Broadcast Studio. Are we still working fine here? It looks like we're still working fine. Cool. All right. Now, I talked about census last time. And a census is where you measure every member of a population. In this country, census happens every 5 years. And census, or censi, or censi, I have to look that up. What's the Latin of census? Plural of census. I think it's censi, but whatever. Anyway, the point is, governments of all sizes need to know how the population changes. And really the only way to understand that without a margin of error of any consequence is to measure the entire population. But the problem with this is it takes a lot of money, it takes a lot of time, and those are the two most difficult things to overcome. You cannot get away from spending a lot of money and a lot of time. And when I say money, I'm really talking about resources, people, tools, a lot of paper, etc., etc. What do we got going on here? Oh, look at that. That's a spam. Okay. All right. Well, I'm not logged in as admin, so I'm not going to be able to nuke that, but it's okay. We'll get rid of that later. Okay. Spammers die. Can I say that? I just did. Okay, what's a sample? A sample is a subset of a population. That's what it is. It's a subset of a population. And if we do the survey with a degree of care, in other words, the survey observations, participants are selected randomly, and by random that should also imply that they'll be independent of each other. We're going to talk about what independent means, and therefore we should have a representative sample. Then the sample can be very, very accurate when it comes to reflecting the characteristics that we're interested in that describe our population. So this course, we're going to eat, drink, breathe, and excrete samples. Well, you can't, constant intake has to be followed by constant output. Anyway, the idea of sampling is the main part of this course, is how to do it, what to look out for. So we're not going to spend a lot of time on that definition right now, because I want to move on. Anyway, so census, to summarize then, is expensive, time-consuming, but very accurate, but you have to measure every member of a population. A sample then is a subset of a population and costs far less resources to acquire, and if done carefully, will provide accurate characteristic estimates. When I say characteristics, average values, standard deviations, all the typical things that we want to know about. Moving on. Random sampling variability. I hinted at what I usually mean, well, what I always mean when I use this phrase. It's my own personal phrase describing luck. You cannot escape luck or chance when you do statistics, because of this, randomness. We can't control randomness. Think about it. If you could control the randomness of some process, then it wouldn't be random anymore. There's a lot of different ways to talk about randomness. The general idea is it's unpredictable. So a couple of points about randomness, and if you think about it, and how they bear back onto the concept of chance. Dice are supposed to be random. Coin flipping is supposed to be random. If I flip a coin and it pops up heads, that tells me nothing at all about what's going to happen on the next flip. The only thing I know about flipping coins is it's either going to be heads or tails, barring any smart-ass remarks about landing on the edge. Some people like to be like that, but the chances of that are not zero, but they might as well be. So randomness, random events, that means each thing that happens, each event that happens, each data observation that happens doesn't tell you anything about what came before, and it tells you nothing about what came after. And we're in an ad break now, so I'll wait for this to run out a little bit, and then we'll carry on with our discussion about this stuff here. Yeah, there goes the Audible ad. Thank you. Now, we got cars, I think. What are you? Oh, no, it skipped the dishes. Yep. The gal and the driving the car in the skip the dishes ad here reminds me of someone I used to know from years ago. Almost a dead ringer. It's true, everybody does have doppelgangers. Of course, got the smart aleck in the back seat too, but it reminds me of somebody else I used to know. Thing is, if you get old enough, after a while, you start recognizing that, like in the saying about marketing, there are no original ideas anymore. Well, I've got a funny feeling that people repeat too. Anyway, we're almost done here, and we'll get back to our lecture. There we go. Okay, we're back. Okay, so randomness and independence kind of go hand in hand. You'll notice that coming up. Where is the independent one? Oh, there it is. I'm a little bit out of sync on that. We'll get back to that in a minute. So, random sampling variability is something that always comes along due to randomness. You can blame it on chance or luck, be it good luck or bad luck, doesn't matter. I don't think the universe cares either way, quite frankly, but, sometimes humans ascribe to the universe characteristics that it doesn't really deserve. It's a cold, dark place. Anyway, luck and chance. Later on in this course, we'll talk about type 1 and type 2 errors in hypothesis testing. And luck and chance, random sampling variability, are front and center in that discussion, because you can do a statistical survey of some population by taking a sample, and 99 times out of 100 everything will work fine, but you cannot escape statistical blips. A number of years ago there was a provincial election in the province of British Columbia, and right up to the day before the polls, the prediction was that the new Democratic Party was going to win the election. Except those polls, the specific poll I'm thinking about, got it wrong, because they didn't win. One of the other parties won. And this is that statistical blip, the luck or chance. It's like a sports team who's terrible. They may be the bottom team in the league. Whatever it is, hockey's the big deal around here. Although cricket's quite popular in Edmonton too these days. But the point is, the worst team can still beat the best team simply due to, we call it luck or chance, or simply the variability in the play of the two teams. And you can't predict that. And that goes back to random behavior. Anyway, we're not going to get too deep into the mathematics of stochastic functions, stochastic events. Here's a good example of randomness. Diffusion. So here, let me see if I can draw a picture of something remotely interesting here. Let's see here. Let's make a bottle. There we go. Boop, boop, bing, boop. Look at my artistic abilities. Wow. Not only can he do math, he can draw a bottle. And what we got going on here? This is a perfume bottle. You take the top off a perfume bottle. Eventually you can smell the perfume. Actually, when I say eventually, not that long afterwards, you can smell it everywhere because the scent, the scent molecules diffuse out into the atmosphere. And diffusion is a random process. It's not driven by anything. The air around you is nothing but molecules constantly in motion, and they follow what's called Brownian motion. They're random. Good luck predicting the path of any one molecule. You won't be able to do it. It'll do this and then that and then that and then back. Well, anyway, you can look that up online if you want. Okay, enough of that nonsense. Moving on. Boo! Since we were talking about independent and dependent data, we'll talk about this slide next. So independent data and dependent data also touch on the randomness aspect of things. Data that are independent tell you nothing about events that preceded them. They tell you nothing about events that are going to follow them. They carry no information. So no information whatsoever. No information about, I should try to write a little bit better. I'm getting a little bit, okay, where's Control Z? Let's get that out of there. Let's try that again. No information about the past or future events. None whatsoever. However, dependent data does. There's something in common. Now let's finish this off here. No commonality. No commonality between events or data observations. But dependent data does. And it does carry information. For instance, here's an example. Oftentimes on university campuses, everywhere, you'll see a poster. Grad student needs volunteers for their study. And they're willing to, throw you a gift card or something for your participation. Well, oftentimes what happens is someone will see that and they'll say to their friends, "Hey, we should go do this. We can each get a gift card. Go fill out a survey, get measured, or whatever is appropriate for the context." But that group of friends, they all have something in common. They like each other. They hang out with each other. So that makes a cluster of dependent observations that the researcher has to deal with, because these people have something in common. Maybe they come from a wealthy part of town. Well, that means their attitudes are going to be similar. Maybe they come from a social demographic that's unusual in the community. Well, that's going to destroy or certainly damage the characteristic of having a representative sample for your research. So there's ways to handle that by randomly assigning each person to a different group, because this is hardly a new observation about things that can go wrong in sampling. But the point is, getting independent data isn't easy. So dependent data then generally has data, or we can describe as data that has some commonality. Now, it may be that it's trivial, but everything that goes wrong in a study should be written up in the paper that you publish. And the critics of that paper are going to pick up on these things. So it's not something you can just say, it doesn't matter in this case. Well, if you're going to do that, you better think about that long and hard, because it probably does matter at some level. So and so if there's some commonality, then that means there will be information about the others. There will be information. What's the word I'm going to use after that? There will be information about other events or observations. So you can't escape that. Yoink. There we go. Okay, let's move back. Previous. Okay. So, continuing on here. Oh, we're doing all right here for time. This one's probably going to run a little bit longer than an hour, but that's fine. We're going to talk a lot about continuous and discrete data. And there's also continuous probability distributions and discrete probability distributions, but we're going to talk about this in context of data for now. We'll talk about continuous or discrete in context of probability when we get to probability. So what are examples of continuous? Well, anything that can be written to an arbitrary number of decimal points is a real number. So continuous data is often described as a real number. The most likely thing you're going to encounter is the flow of time. Because you can always, the interval between any 2 seconds can be sliced as thin as you wish, and you will always find a number in between any 2 values, which leads us, of course, into a fascinating discussion about the real number line, but I guess we shouldn't go there. So the flow of time is continuous. If you want to talk about the average weight of a person, well, the average weight can be measured as accurately as your machine or your instrument will allow. So you can have as many decimal points of accuracy. So things like weight. Yeah, you can say, well, someone weighs 62 kilos. Yeah, but you're just rounding. You're just dropping the decimals. It's going to be 62 point something, something, something. So there's that. Flow of water, liquids in general. Now I'm going to do something here because I like to mess with people's heads. Liquids flowing past a measuring station, past a marker. So here in Edmonton, we have a very large river that runs through the city, and it's a very fast river. And I always say to people, if you like contradictions or little memory, or what's the word I'm looking for? Little conceptual games. Yes, the flow of water past a bridge piling can certainly be measured as a continuous variable. Liters, gallons, metric tons per minute, per second, per hour, per day, whatever you want. But where things get really interesting, and then we can make a leap over to the business of the physics of the very small. Yes, I'm trying to not use the word quantum. At some point on the measurement scale, the flow of liquids and the flow of gases stops being continuous and becomes discrete. Because if I start measuring the flow of water past a bridge pylon, measured in discrete molecules of H2O, it's no longer continuous because water doesn't flow as 2 atoms of hydrogen and 1 of oxygen, or however you want to split that. So yeah, eventually if you use a fine enough filter, continuous becomes discrete. What is Planck time? Okay, here's a Wikipedia rabbit hole for you. So we're talking about Mr. Max Planck, and what is Planck time? Because I always said up here that time was continuous, but is it possible that Planck time is a discrete and smallest unit of measure for time, the flow of time? So if you have Planck distance, the Planck length scale, yeah, I'm getting way off course here, but enjoy the rabbiting on for what it is. If we call Planck time the time it takes for the speed of light to traverse 1 Planck length, then we have an absolute minimum for the smallest measurement of time. Okay, I'll leave you to chew on that one for a while. Now, so you'll notice that all these things become discrete. Let's make another note here, real numbers. In other words, decimals. Well, over here we have integers. Discrete data, integers are often measured in integers. 1, 2, 3, 4, but nothing in between. So when you count people, when you count individuals, you have discrete data. People are discrete. Well, at least they are as data points go. People, any object that you can hold in your hand would be a discrete object. You know, if I wanted to talk about discrete in context of the river, well, ice breakup, you can count the number of ice chunks flowing past a piling for a bridge. You know, people and things. So generally speaking, if it doesn't make sense to divide something, then it's probably discrete. There's exceptions to that, though, because you're saying, well, wait a minute, earlier I did the uniform distribution for the roll of a die, right? And I came up with the average value of 3.5. Well, the average value is not a number on the die, right? Because you got 1, 2, 3, 4, 5, 6. But I got 3.5. Yeah, that's where things get kind of silly. So again, you got to think about this a little bit. Not the end of the world. But nothing is cut and dried as much as some of the concepts that we're going to wrestle with. Anyway, this course isn't going to break your brain, and there's other ways we can cut this stuff up finer. There's an old saying, no matter how thin you slice it, it's still baloney. You know, I suppose that's another way of saying if you put a dress on a pig, it's still a pig. It's just a pig in a dress. But yeah, let's move on. Qualitative versus quantitative. So this goes hand in hand with our discussion on the slide we just left. Qualitative data is oftentimes, I call this categorical data, because it's easy to understand. Because categorical, I have a hard time spelling this word, by the way. I don't know why. Categorical data is anything that's named. So categories, days of the week, right? Days of the week. That's a category. Things that happen on Mondays, well, that's a category, right? Color. A status. Things can be on or they can be off. They can be alive or they can be dead. To go back to the previous lecture about zebrafish. So anything that has a name is generally qualitative data or categorical data. The one thing that keep in mind here is it doesn't make sense to try to find the average value or the standard deviation for that matter with raw qualitative data. So how should this, let's write mean and standard deviation are usually not used. How should we word that? Mean, standard deviation, not useful here. The example I'm thinking of when I say not useful is, what does it mean to take the average of 3 colors? Well, let's not go into color theory. But if I said to you, what's the average of the days of the week? Or there's any number of things that it doesn't make sense to ask about. I'm looking at the word color I wrote there, and I'm going, I don't know what the hell I wrote there. Let's try that again. Colors. There we are. That's better. So qualitative data is things that have names. The most we're probably going to do with them is turn them into percentages, but we'll leave that for another discussion. Quantitative data here, it certainly does make sense to talk about the mean and the standard deviation because you can do arithmetic with this stuff. Okay? It means something to, if I give you a set of numbers and say, well, what's the average value? Well, you can figure that out. We did that earlier. So quantitative data can be integers, certainly. We did that earlier with that example. or real numbers. Just in case you have a prof that's doing math notation, integers are typically capital Z, and real numbers I'm sure you've seen as capital R, but they're stylized. So if it's meaningful to do arithmetic, specifically division, you're probably dealing with quantitative data. All right. These things will make sense as we make our way through various bits and pieces of this course. How are we doing on the clock here? Well, we're about an hour in. Got a couple of slides left. We're almost done here. Biased versus unbiased samples. Okay. We talked briefly about bias last time. So a biased sample usually means that the sample is not representative of the population. Let's write that out. Representative. Am I even spelling? That's good enough tonight. Representative of the population. So if the population is an average of 72 kilograms and your sample has an average of 43 kilograms, it probably is incorrect. It's probably a biased sample due to any number of reasons. Bias can happen from sampling errors, could be a measurement error. There's all kinds of reasons for a bias to creep into a sample, including random sampling variability or chance. Sometimes you just end up with a set of numbers that doesn't make sense, and that's something statistics has to deal with. Example I use oftentimes, you can, any one day over a semester, you can pop into, say, the student union building on campus and get an average value of shoe sizes. But if you pop in there when there's a basketball tournament in town, you're probably going to find the feet are, on average, quite a bit bigger. And again, that's bias. An unbiased sample, then, is where you have a representative sample. Usually it's the standard, or not the standard deviation, usually it's the mean value that indicates that something's not right, but other measurements can also be out to lunch as well. So, I mean, you can have two populations with, I'll draw a picture of this, but you can have two populations with the same center that have vastly different spreads, and then you go, well, is this actually, this sample representative of that population or not? Let me write this out first. Representative. Representative of the population. Okay. So let's make two bell curves. So here is a bell curve with a narrow spread. Most of the values are close to the center. That's why we have this tall, narrow curve. And this might be mu, which is a symbol for the population mean, might be 10. But then we may have one over here. This one can also have a center at 10, but this one's considerably wider, so its spread is not representative. So if this is sample A, this is sample B, or population A, population B, if you want to go that way. The thing is, the centers of A and B are identical, but the spreads are significantly different. And then you have to ask yourself, are they really the same population? Probably not. Let's say that this is the true population distribution. This is the distribution of the sample. Well, one of the properties says that the centers are going to be the same, but how does a sample get to have this much wider distribution here? That doesn't make sense. It means that something's not right. So that's a topic that we'll discuss more a little bit later on in the course. I just wanted to illustrate right now that an unbiased sample means that the sample is representative of the population, typically the means or the standard deviations. A biased sample means those two things are not representative of the population. That's a midterm question, by the way, just so you know. All right, here we have clusters. So this is one of the little discussions about sampling. We'll talk a bit more about sampling as well. For the courses that I'm thinking of here in Edmonton, at the universities here, usually this is assigned reading. I don't talk about it in class too much. So I want to clarify cluster sample versus stratified sample. This is a very poor example of the shape of the province of Alberta. The squares represent communities that have a hospital capable of doing surgery. It's just, I think there's, 9 of them here? 4, 3, no, there's 10 of them now. It's not fully representative. I've left a couple of communities out, but it can make these pictures too much. So the difference between cluster sampling and stratified sampling is where the randomization occurs. In cluster sampling, we're going to randomly select a subset of the hospitals. Maybe let's get a different color. Maybe I will select this community, and this community, and this community, and this community. Once I subset the hospitals, a random selection of hospitals, then I'm going to go in there and do my survey of every patient in the hospital. I'll do a census in each one of these hospitals. That's cluster sampling. If I'm going to do stratified sampling, I'm going to sample all the hospitals. So that means every one of these hospitals is going to be included in the sample, but I'm going to subset using the patients. So I might randomly select. We want to, because hospitals are different sizes, we're not going to specify a number, we'll specify a percentage. We're going to randomly select one patient in 4 or one patient in 10, but we will specify how to randomly select the patients in the hospital. So if you're trying to find a way to remember the difference between cluster samples and stratified samples, it's where the randomization happens. Clustering happens by subsetting, randomly subsetting the hospitals or the locations, and stratified is you're subsetting the population in all the hospitals in this context. There's typically a question about this that oftentimes shows up talking about drug testing on sports teams. Well, we could subset the sports teams and then test all the players on that subset, or we can take a subset of every team's players. Again, cluster versus stratified. The reason I bring this one up all the time is it's a lovely little question on the midterm exam, because no one ever does the assigned reading. Not judging, nothing like that. Okay, there we go. Those are the topics I wanted to talk about. It's only an hour into the trip, so yeah, that worked out just fine. Just going to add another slide here. So next time, the plan for next lecture is going to be descriptive statistics. I might talk a bit more about different sampling techniques. I think I will, actually. But I'm not going to make it an entire hour-long chat. So we'll talk about descriptive stats and some more chat about sampling. But as far as methods, as far as definitions go, there's more definitions to talk about, but they're not relevant until we get a bit further into the course, so I'm going to leave them for now. So this is what we're going to do next time on the Tutor Wizard when we do our next statistics lecture, which is going to be the working day that I'm thinking of is going to be, where's my calendar here, is going to be on the weekend. I normally do stats on what's a Saturday afternoon, but that's the date for Saturday afternoon. That looks like May the 3rd. So that's the tentative next statistics discussion. Okay, thank you for joining us tonight and for putting up with my chitter chatter pitter patter. I use Open Broadcast Studio, as you can see, to run this thing. I do appreciate you hanging around tonight, and if you want to review this video. Obviously, this stream will be archived on Twitch, but it's also going to be archived on our YouTube channel. It's the same name, The Tutor Wizard. And you go to the stats playlist, and this is where I'm going to have them all show up. Actually, I think we changed. Just look at the playlists. There will be a playlist for these lectures. And let's leave it there. You folks have a great night. We're going to do some other interesting things. Lorenzo's flying tomorrow. He's going to have a lecture. And we'll also have more of the history of mathematics coming up on the weekend as well. And then we're going to do some random game streaming as well. Oh, here comes a kitty cat. I have to get my camera set up here so you can meet the cats one of these days. Anyway, this is Abigail. She's a house panther. Looking to crash on my chair over there. Cool. All right. Hey, listen, thank you tonight. And if you want to review this stuff, like I said, look at YouTube, look at Twitch. And if you're on YouTube, give us a like. I appreciate that. We're trying to get this show to roll in a profitable way so that we can, get through the intercession. Terrible time for academics because not a lot of teaching going on and we have bills to pay too. All right, enough of that. Have a great night, everybody. Talk to you soon.